Let's now go over resistors in series and parallel. When the term series is used in circuits, it's referring to when two resistors each share one terminal together. So here I have R1 and R2. So our goal here is to calculate what the overall resistance of this two resistors is going to be now. So what we can do is place an ohm meter around them and see what our R equivalent is going to be. Now, ohm meters are just voltage sources. So there are voltage sources that create some current I, and what they do is they say, okay, I know the voltage I'm creating, and I can measure the current that is created when I connect to these two resistors. So I'm going to divide my voltage by the current, and using Ohm's law, I'm going to get R equivalent. But let's derive this equation. So we know that from first lecture that my overall voltage of the voltage source of the ohm meter is equal to the individual potential differences consumed by the resistors. So by resistor 1 and by resistor 2. Now, using Ohm's law, I can say that, hey, my V is equal to I1 R1. This is the current going through resistor 1 times resistor 1 plus current going resistor 2 times resistor 2. And then what I can say next is that, hey, there's nowhere for my current to escape, then I1 must equal to I2. There is no alternative path for I to escape. So now I'm going to say V is equal to I R1 plus I R2. And then I'm just going to factor out. And my V over I, which is equal to R equivalent, is going to be R1 plus R2. So series resistors simply add their overall resistance together. And similarly, when two resistors share both their terminals together, they are now called resistors in parallel. So again, we want to know what the entire resistance of the circuit is, so we're going to place an ohm meter. So it's going to tell us R equivalent, which is equal to V over I. Now I have my V over here that the ohm meter provides and the current. So I need to simplify some stuff so I can derive an equation here. What I'm going to say is that this entire node has the same potential energy, right? Why? Because in this node there is no resistive elements, there is no load consumption elements. So my V has to be V everywhere. And likewise, this entire terminal has the same potential energy. So now, what is my potential energy difference across the resistors gonna be? Well, since they're sharing terminals with my voltage source, it's just gonna be V across both resistors. Now I'm gonna say that my current I is equal to I1 plus I2. What is I1 and I2? When current reaches this point over here, it splits into the current that goes in resistor 2 and current that goes in resistor 1. It's not like the series anymore. These two resistors might have different currents in them. Now, with Ohm's law, I will replace I1 and I2 with V over R1 plus V over R2. Why? Because I know the potential difference across them. It's just V. And then I will factor out. And then I'll say I over V is equal to 1 over R1 plus 1 over R2. And what is I over V? It's not R equivalent, it's 1 over R equivalent. So 1 over R equivalent is equal to 1 over R1 plus 1 over R2, which can be simplified to R1, R2 over R1 plus R2. Let's see if we can relate this equations to what we learned in resistivity section. So there we said that all the wires can be modeled as resistors, right? Because they have some resistivity rho to them, some length and some area. So let's say we have two resistors here and they have resistivity or same resistivity, length and area, so they're basically the same resistor, equal. Now according to our equation developed, our R equivalent should be R1 plus R2. Well, let's see. If I connect these two wires together, I'm getting a wire twice the length with same area, a resistor twice the length, same area. So my R is going to be, R equivalent is going to be rho 2L over A is equal to 2 times rho L over A. So it's just 2 R's. So yes, our equation stands here. And now let's say we connect these two resistors in parallel. So our equation tells us that our equivalent would be R1 R2 over R1 plus R2. And that's just, since R1 and R2 are equal, it's going to be R squared over 2R. It's going to be R over 2. Well, let's see. Is it R over 2? If I connect these two resistors in parallel, it's like this time I'm increasing their area instead of their length. So our equivalent resistance now is going to be rho L over 2A is equal to 1/2 rho L over A. So it is R over 2. So it does stand here again. Let's create a short example now. Let's say I have a 100 ohm resistor here and a 10 ohm resistor here. So I want to know what happens when I connect these two together in series and in parallel. So first, I'll connect these two resistors to a 100-volt source separately. And my current for each one of them is going to be 100 divided by 100, 1 amps. 100 divided by 10, 10 amps. Now I'm placing them in series. I'm applying a 100-volt energy to it. So now my current is 100 volts divided by 100 plus 10, 110, which is approximately 0.91 amps. So notice when I connected in series, the overall current was less than both of these currents. Now let's see what happens when I connect them in parallel. So I know I'll be getting this I over here, and it will split into I1 and I2. So I know that there's 100 volts across each one of these two. So my I1 is 1 amp, 100 divided by just like this case over here, and my I2 is 100 divided by 10, so it's 10 amps. So my overall current is 11 amps. So compare this two with this two. So in series, my overall current was less than the individual currents, whereas in parallel, my overall current was more than each one of those currents separately. Why is this? Because my R equivalent over here is R1, R2, which is 100 times 10 divided by 100 plus 10, and that gives me 9.1 ohms, whereas here my R equivalent is 110 ohms. So in series, my overall resistance increased, whereas in parallel, my overall resistance decreased. It's smaller. 9 ohms is smaller than my lowest resistance, 10 ohms. And that's the best part about parallel resistors. When you connect two resistors together, the overall resistance is going to be smaller than or equal to the smallest resistance in your circuit, in this case 10 ohms. Therefore, if I had n resistors in parallel, then my overall resistance of the circuit would have been smaller than or equivalent to the smallest R existing in the circuit. So if I am to create a equation for n resistors in parallel, that would be 1 over R equivalent is equal to 1 over R1 plus 1 over R2 plus dot 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 plus 1 over Rn, which we can simplify with a summation notation. From 1 to n, addition of all of them. And for series, it's much more simpler. If we want to develop a summation equation, it's going to be summation of all the resistors. And let's wrap up today with a very simple example. It's asking us what the equivalent resistance is from point A to ground. So from point A, I'll place an ohm meter to ground, and what is my R equivalent? So don't let grounding confuse you. You can just connect all these grounds with the wire together and solve it like a regular circuit. So in order to solve the circuits, you should start from the farthest point from the ohm meter you're trying to measure the resistance of. And this is the farthest point. So I want to replace these three resistors that are in parallel. Why? Because they're sharing both their terminals together with their resistor, Rx. So what is my Rx going to be? It's going to be 1 over Rx is equal to 1 over R plus 1 over R plus 1 over R. So then my Rx is R over 3. If you simplify this equation. So now my circuit looks something like this. I have from point A, resistor here, a resistor here, and I have my Rx, which is R over 3. Now I know that this resistor and this guy share one terminal together, so they must be in series. Then I'll take these two and I'll add them because they're in series, and I'll get 4/3 R. So then my circuit is going to look something like this. I have R and equivalent resistance of 4/3 R. Now these two share this terminal together and ground. I said you can connect grounds with the wire, so they're actually sharing that node together. So then they're in parallel. So my final resistance I can replace this entire circuit with is going to be 4/3 R 4/3 R in parallel with R. So that's 4/3 R squared over 7/3 R. Using the parallel equation, can cancel out some stuff, and I can get 4 over 7 R. So my resistance from point A to ground is 4 divided by 7 R. So if you were to write an expression for this entire calculation, you could do the following. You could say R equivalent is just starting from the farthest point. We have 3 resistors in parallel, series to a resistor, which is then parallel to another resistor, and this gave us 4 divided by 7 R.